Alright, in this video we'll be going over the skills check for Chapter 4, a chapter where we're going to be doing a lot of graphing, and so it's important you have some basic skills that you would have seen in a college algebra course. So let's go ahead and go through this. So first of all, it says without graphing, determine whether the equation has a graph that's symmetric with respect to the x, y, or y-axis, the origin, or none of these. I'm going to actually change this just a little bit. We're going to write it as f of x equals x squared plus 15. And what we've learned, or what you should have learned in college algebra, is if you replace x with minus x, let's go ahead and do that. Notice what happens here, because when you multiply two negative x's, this is negative x times negative x, you're going to end up with a positive x squared plus 15. And so when we plug in minus x, we end up with the original function, f of x. And so anytime that happens, you have what's called an even function. And that means you're going to have y-axis symmetry, which is what we have right here. Now, you may recall, basically this is a parabola. Y equals x squared looks like this. And if this is 15 on the y-axis, then this is just the same graph shifted vertically up 15. And you can see the y-axis symmetry. You know, this point here is a mirror image of this point over on the other side here. They both have the same y values as well. Alright, let's look at number 2. It says determine whether the function's even, odd, or neither. So again, we'll plug in minus x. And let's see what happens when we do that. Well, when you multiply 7 negative numbers, you're going to have one. Well, basically for every pair, negative times a negative, you're going to get a positive. You're going to have one leftover negative minus x, and so we're going to end up with a negative number here. So this term becomes negative 2x to the 7th. The same thing happens here. Multiplying 3 minus x's will give you a minus x cubed, which is going to change the sign here. It'll become a plus 3x cubed. And what's happened here is you'll notice compared to the original function, we have the opposite signs. In fact, we can write this as the opposite of f of x. And anytime that happens, we have an odd function, which means we also have origin symmetry. Probably one of the most common functions we look at with origin symmetry is the graph of y equals x cubed, which will look something like that. And you can see that basically if you have a point anywhere on this side and you cross the other side of the origin, you'll have a point the same distance away. And so you have this origin symmetry, literally symmetry through a single point. All right, let's look at number 3. It says graph the function. I'm going to use a different grid. And notice this is the graph of x squared, but it's got 3 out in front. That's going to cause what we call a vertical stretch. And I'll show you why. So if you were to graph y equals x squared, I'll go ahead and do that with little x marks. You would get these 5 points. If you plug in 2 to y equals x squared, 2 squared is 4. And negative 2 squared is also 4, and so the graph of y equals x squared would look like this graph here. I probably should have just made this a dotted graph. And so how does this graph compare? Well, if you think about it, you're still squaring your input, which is x, but the last thing you're doing is multiplying by 3. So all your y values are going to be 3 times as big. So instead of being at 1 here, you're going to be at 2. Of course, 3 times 0, you're going to end up at 0. Well, let's see. Instead of being at 4, we're actually going to be at 12, somewhere way up here. We'll just estimate. And so you get a graph that's much more narrow. So we call this a vertical stretch. You can see that these two sides here are stretching towards the y-axis. If this had been a number like a half, it would have been a vertical shrink and we would have a more wide-looking graph. All right, so that's what we call vertical stretch. Let's move on to number 4. So hopefully you know what this one looks like. Again, I'll use some different graph paper here. So again, we know x squared is here. How is this graph going to be different? Well, anytime you have a number that's separate from the part being squared, this minus 2 is going to cause a vertical shift. And it's going to be down 2. I'd like to use a little arrow there. And so we just basically take each of our points and move them down 2. It's basically the exact same graph moved down 2. Normally what I do is I just take my vertex down 2 and I draw the same shape. Now if this had been a plus 5, we would have taken this graph and moved it up 5. So I think vertical shifts are very intuitive. You know, if this was a plus 10, we would move the same graph up 10. We had one where it was x squared plus 15, we were up 15. If this was a minus 7, we would move our graph down 7. So again, it's very straightforward, very intuitive. Horizontal shifts are a little bit different. That's what we're going to look at next. So on number 5, and it's getting a little harder here. Let's see, I can, let me fold this. There we go. Okay, so hopefully you remember what that looks like. I'll let you maybe give that a try. Again, our original function looks like this. That's y equals, or g of x equals x squared. And it turns out this is going to be a horizontal shift. And these kind of work the opposite or backwards to what you might expect. Because I'm looking at this plus 3. Now notice it's the difference between this and what we were looking at before is this plus 3 is inside with the x. It's part of what's being squared. You can easily plot points by plugging in some x values, but all to say what you find is you get a graph that's horizontally shifted. Now because of the plus 3, I would think it'd go to the right 3, but it's actually the opposite. We're going to go 1, 2, 3 to the left. And basically each of my points moves 3 to the left. I just like to draw the same shape over here. And so your graph would look like this. All right, let's move on to number 6. It says complete the left half of the graph of y equals f of x and the figure for each of the following conditions. All right, so if f of minus x is equal to f of x, Remember, that's where we have an even function and we have y-axis symmetry. So basically, we would just reflect each of these 3 points through the y-axis. Well, this one's on the y-axis, so it doesn't move. This one would go here, and this one, what's that? 1, 2, 3, 4. We're going to go 4 on the other side of the y-axis, and it would look like this. So it's going to be letter C. Now, notice here, this is like the other one that we did. I think it was number 2, where this is, when you plug in minus x, you get an output of minus f of x. That's how an odd function works. And that's where we have origin symmetry. All right, so if you come down here, well, actually, let's just erase what we did here. So we're going to reflect all of our 3 points across the origin. 0, 0. Well, that point won't move. This one, we're going to go 2 on the opposite side. That puts us here. And let's see here. Let's see. We're 1, 2, 3, 4, down 1, 2, 3, 4. So we're going to be, if you go through this line here, we'll be at 1, 2, 3, 4, 1, 2, 3, 4. We're going to be on the opposite side. And so you can connect these points, and your graph's going to look like that. And you got to be careful here. It's going to be one of these first 2. Oh, this one's the right one because that point, this point's off, so it would be B. All right, let's move on to number 7. So there's a few functions that you should be familiar with. The absolute value function, well, we already talked about the x² function, where you get a graph that's a parabola. If you have the absolute value function, let me move this just a little bit. Maybe too much. So basically it says, okay, so this graph is obtained from the absolute value function, or actually it also mentions the square root function. Well, these are the two functions, two of the functions that you ought to be familiar with. The absolute value function is V-shaped, and it looks a lot like a parabola, but it's V-shaped. And then this is the square root function, which looks something like that. I call it the ET function, or the Superman function. You remember ET, the big long finger? But this is obviously the one we're working with here, and you'll notice it's upside down, which indicates we have a reflection. So it's reflected through the x-axis. And that's our most common type of reflection that we're going to be dealing with throughout this course, and we did in college algebra. And then it's certainly been shifted. Now normally the graph, I think I can just use this, what we already have here. This graph normally looks like this. So if you reflect it, it would look like that. It'd be going down, and that's the shape we have here. But notice we also have gone 1 left and up 4. So it's a vertical shift we said up 4. Whoops, I lost my light there. And a horizontal shift and that's left 1. So we need to put all that together. And so what we have here, well, let's see, actually we need to fill this out. It's the graph of f of x equals absolute value of x, translated blank units to the left, that would be 1, and reflected across the x-axis. I always do reflections first, but they're doing the horizontal shift first, and then we're also going up 4 units up. So the equation well, let's see. We're going to have a minus out front because of the reflection. Because it's 4 units up, we'll have a plus 4 here. And then the horizontal shift, remember that number is going to be inside with the x. Well, it was 1 unit to the left, which normally I would think that would be a negative, but that's going to be a plus 1. So you can always go in reverse if you just want to double check yourself. Notice the plus. So first of all, it's reflected because of the minus. And we already talked about the fact that it opens down like this. Its vertical shift is up 4, and that plus 4 tells me that. And again, a plus 1, it doesn't take me to the right, it actually takes me to the left, so that's correct as well. And so that is our final answer. All right, let's move on to number 8. Use the graph to determine the open interval on which the function is increasing. When we talk about increasing or decreasing, it's always on an open interval. So basically we're increasing, if you look at this graph, it's increasing until you get to this point here. In fact, I like to draw a little line, a vertical line right down that. And you can see here that the graph, or the y values, are getting larger as you go from left to right here, or we say the graph is increasing. And then it starts decreasing at this point. So increasing here, decreasing on this side. Now we describe where we're increasing over an interval of x values. So basically when x goes from negative infinity until x gets to 0, this graph is increasing. And then after you get to 0, from now on it's decreasing when x goes from 0 to infinity. And so this graph, so let's see, it's increasing on the interval from negative infinity to 0. And then if you look at number 9, actually it's a little different graph, so we will have a little bit different situation there. So notice here the turning point is right here, and this graph is decreasing here. So when x goes from negative infinity until you get to 0. So again, as our x values go from negative infinity until x gets to 0, our function, notice the y values, they're getting smaller. We say the graph is decreasing. It's falling from left to right. This other one, it was rising from left to right. That's an increase. And so this is decreasing from negative infinity to 0, and then notice it starts increasing. Now, the reason why this is an open interval, when you get to 0, are we increasing or decreasing? Well, it's really in the middle. We're decreasing on the graph until we get to 0, but after 0, we're increasing. So at 0, we're not really increasing or decreasing. That's why we have a parenthesis here and not a bracket. All right, last problem. Let's see, determine the intervals of the domain over which the function shown to the right is continuous. Well, notice it's continuous except at this point right here. So this goes forever left, so from negative infinity until we get to x equals 1, I believe that's negative 2. Notice at 2 there's no point, at negative 2, and so then we're going to union that with negative 2 to infinity. So what we're really saying is, I mean, if this had just been a line with no hole in it, our domain would have been all real numbers. It goes forever left and forever right. If you look at all the points on this graph, we're hitting every x value. However, when x is negative 2, there's no point here. And so this means our domain is basically everything except for x equals negative 2. All right, and that's going to be it for this video. Let me go ahead and stop.